Okay, so welcome to this meeting where people keep dropping in. Um, we're going to talk about some things that, I want to talk about some things that I learned working on Redis performance issues from the application side. So the background here is that the scalability team has over the past couple of years looked at Redis saturation problems several times where GitLab.com Redis servers would run out of CPU capacity. And one of the things we were sometimes able to do about this was to change the queries that the application makes so that we use less CPU on the Redis server. And I got to work on these types of problems a couple times. So if you do something more often, you learn more, it gets easier every time. And I wanted to use this opportunity to share some of what I've learned from working on this type of problem a couple times. So I'm going to share the browser so I can show you the document. So what the starting point for these problems was every time like one of our Redis server is spending too much or is running out of CPU headroom. And then we need to find out what's going on. And there are a couple data sources that ended up being very useful. And I just want to talk through these data sources. The first one is Redis metrics. These come from the Redis process itself. Redis has a bunch of metrics that it keeps up to date, and you can access them. You get them via the info command. And it has subcommands, and one of them is called command stats. So that is somewhere down here. And it's very simple. So it just says for each command that it's observed, how many calls there have been, how much total time there's been spent in there, and a couple of other things that are not so useful in our experience. So these metrics are there, and they're cheap because Redis has them anyway. And on GitLab.com production, we use something called Redis exporter, which reads these metrics from Redis and exposes them as Prometheus metrics, and then we scrape that into our Prometheus setup, and then we get these metrics and we can query them. And they change names. So in Redis, they're called CMD stat underscore. So this might be get for get metrics. And then in the Redis exporter, the count is called Redis commands total, and the time spent in them is called duration seconds total. So the unit also changes from microsecond to seconds. And then we have dashboards, and there they have yet another name. So they're called operation rate per command and total operation latency. And this average operation latency is kind of useless, and I always wondered why it was there, and I realized it's there because Redis exposes it itself. So we probably just put it in there because Redis has it. But this is almost always useless. So these two graphs really are a good starting point, this one and this one. There's not much to see on these graphs, so there's nothing interesting to see because I'm not aware of there being a problem with this particular server now. I was looking for historical data from some of the problems I've listed further down in the document, but I can't find it because somebody removed the historical data from Prometheus. Bob is smiling because he probably knows why that is, or because he is the person who did that.
I was involved in the discussion and I said 1 year is enough.
Yeah, okay, so now I'm out of luck. Or I don't know how to get to some of the data I still want to show, but that's okay. These graphs are cheap, and as long as it's 1 year or Bob doesn't change his mind about how much is enough, you have easy access to these metrics. And if there is an incident where the Redis server is running hot, you can go back and look at what these metrics were at the time. So they are, and they're also, we don't have logs. You don't have access logs for Redis because that would slow Redis down. So they they should be one of your first. They're the easiest thing to look at if you want to know what's going on and where time is being spent. And the most important one is this one, the total operation latency, because it's, well, Yeah, it is, because it shows you where most of the time is spent. And then you combine that with looking at this graph where you see the rates. Okay, so those were my points about those metrics. The next thing you can do is to look at flame graphs. This is really useful, but it gets more complicated because you need to run a command as root to capture a flame graph. And we have a setup that does that once every hour, but not a lot of people can get to the output from that script. And it's also harder to pick a good time to run the profile. And that's another problem you have with these profiles. You need to pick it. You need to decide, I want to see what the server is doing now, and then capture a profile. And they're usually 30 seconds. The good thing about flame graphs is that they don't contain sensitive data, so you can share them with other people. You can post them on issues. And well, if you don't know what a flame graph looks like, I just captured one for Redis Psychic. So this shows the whole server, what it was doing over 30 seconds, and then the main Redis process was doing this roughly. So, and what's nice about flame graphs is that you can see that Redis is spending time on I/O, which is not visible in the metrics. And you can see what internal functions Redis is spending time in. So this can give you a hint as to what is slow or what is going on. So this gives you a lot of extra detail. And another
One
thing,
thing
yeah,
worth noting is if you zoom back out to the full Redis server process, you can also see time spent in kernel. So I just wanted to also highlight that.
yeah, right. And you don't see that here because this is not doing I/O, but somewhere here where you see these underscore things actually do syscall libc write. So somewhere here, K, I guess case is right. What do you think, Igor? That's probably the kernel.
Yeah, I guess entry syscall is probably where it starts. Yeah.
Yeah, I don't know if this is libc. This looks like it might still be libc, but yeah, this gives you an indication of what the kernel is doing, which is also super useful. Yeah.
From this flame graph, which part of this, I have a suspicion, but which part of
Yeah,
this is on the Reddit's main thread? And yeah,
the whole
should you?
thing. This is the main thread. So there's the IO threads. I don't think, yeah, they show up separately, and they're not doing anything in this case. Although when you do a background save, actually you can't really see it that well because background saves would also show up here because they fork from main, I think. So in the case of IO, Redis IO threads, you can see, but it's not always clear. But what I wanted to say about the metrics, so this command duration total, where is it? Here, this total operation latency shows time spent in BR pop, L push, L rem set, and oh, now Zoom is blocking my tabs. So that corresponds to this thing here, call, which is the function in Redis which handles individual calls. So here you see time spent doing an LREM, doing a push, doing an eval, doing a blocking pop. So these little blocks and their width correspond roughly to how high these graphs are. So you can sort of map the commands you see in these graphs back to how wide the bars are here. But what's great about the flame graph is that there's stuff that happens outside call. Actually, most stuff happens outside call if you see how small call is compared to the rest around it. And sometimes you can find an interesting problem that happens outside of call by looking at a flame graph. And a very good example of that was the work we did on switching to a small number of psychic queues, because there's this function handle client blocked on keys. This flame graph is from Redis Sidekick. And this thing was very busy, and that was happening outside of the call, the call statistics. So what else did I want to say about flame graphs? Yeah, so you see more, but the problem is you need to decide to capture them and you need access to capture them. This is something we could fix over time if we make higher frequency periodic profiles, so we give more people access to them. But right now, we don't have that. Then next up is TCP dump traffic capture, which is super, super useful. But again, it's only there for people with root access. You need to do it on demand. And it contains sensitive data because you're basically seeing everything that goes in and out of the Redis server. And so you see too much data, really, because from an application viewpoint, what I usually care about are the keys or just patterns in the keys, and you don't need to see the full keys. And I was saying there's no access log, so this temporarily creates an access log where you can actually see what is being done on the Redis server. So as far as I think right now, this is the only way you have to see patterns in key usage. And the other way around, if you see like there's a lot of get calls on this Redis server, like what keys are they getting, or what application code is doing that? In order to find out, you need to know what keys are being accessed. And the only thing we have for that right now is TCP dump. And in the cases where we did work to reduce the number of requests, it was always crucial. Like sometimes you look at these graphs and you would see like, oh, there's a funny command that's being called 10 times more than everything else. And it is so unique that there's only 2 places in the application where that command gets called. So then maybe you can find out just by the name of the command where it's coming from. But often that's not possible. So you need to also know the keys that are being fed to the command. And once you know the keys and once you know the pattern, you can use grep in the GitLab code base to look for the key pattern, and then you find a Ruby file where we make those calls. So yeah, and when I worked on this, I was sort of in a uniquely advantaged position that I had root access, so I could grab these profiles whenever I wanted. And I've experienced making application changes, so I could then go off and make application changes. And with the traditional split of roles, this is harder to do. And I want to finally mention there's also Redis CLI monitor, which gives you kind of the same information as TCP dump, but it has too much overhead for production, so we don't use it there. But once you've found a problem, you're working in development, you want to see if you're making a difference, then you can use Redis CLI monitor. But the kind of problem I'm talking about here is something's not right in production, and we need to find out what. And Redis CLI monitor is not appropriate for finding out what's going wrong in production. Any questions so far? Okay. Oh, and yeah, please interrupt me like what Igor did. That's great. I'm happy if people have something to add or ask. So from doing these things, I came up with a couple of principles, and I have a couple of examples. So I think we're going to start with the principles because I put them in that order, but and then talk about the examples as they come up. So one thing that it took me a while to learn, which seems obvious in retrospect, is that fewer requests is better if you want to make things get the CPU utilization down on the server. And that is because apart from time spent in the call handler, every request has overhead for doing I/O. And that goes back to what we saw here in the flame graph, that call is actually a tiny piece of the work. And there's also read query from clients and write to clients. So every time the application does another request, that means more time spent in write to client and read query from client. So if you bring down the number of requests, you reduce time spent in the call handler, which is like the most obvious place, but you also reduce time spent here. That's good. Although the bad news is that it can be hard to predict how much time you're reducing here. And that's because of the I/O threads that Bob mentioned. So on this server, they're not doing anything. But when they're active, what can happen is that you're reducing time spent. Writing data to clients, but the time was off the main thread. So you're actually not bringing the utilization of the main thread down. But there's a multiplier for every request you shave off, but you don't. It's really hard to say upfront what the multiplier is.
I guess one additional thing here is that you can batch requests together, and there's two ways: either using something like a multi-get or using pipelining, and both of those techniques don't necessarily reduce the number of requests, but still help with reducing the overhead per request.
Yeah. Yeah. I have some more. Actually, I have something about multi as the next talking point. That's yeah. Of the two, my preference would be right now would be single commands that fetch multiple things over using pipelining or multis. So yeah. So one thing I learned or I decided from the things I worked on is that I find multi suspicious because if you have something that, well, the example for this is duplicate jobs. So we have a duplicate Sidekiq job deduplication middleware, and that needs metadata for each job, and it runs when each job gets scheduled, and it runs again when it gets picked up and when the job is done. And at one point when we started looking at this thing was using 5 or 6 or even more different keys that it had to set and read and delete before and after each job. And we changed the query so that all the data lives in just one Redis key, and that brought down the number of calls, and that had a big impact on the CPU utilization of the server. But that was a multi, and it was so it stood out that, like, why do we need a multi? So Redis multi is a mechanism for doing transaction-like things, right? A single Redis call is always a transaction in the sense that nothing else can happen at the same time. But if the application sends 2 calls after each other, something might happen in between, and multi prevents that. But yeah, if you're writing application code that uses a multi and it's on a hot code path, and your multi does 3 things, then you're doing 3 calls every time you need to do your thing. So that acts as a multiplier. And multis are pipelined, which Igor just mentioned. So pipelining reduces the I/O overhead. But yeah, in the case of duplicate jobs, it still helped a lot to just get rid of the multi and do things with one call. So what that looked like in the code, I have that somewhere with the where is it? Yeah. So the old code we had there used a multi, and it did a set, and then it called this method, which we'll jump down to in a moment, and then it did a get, and this check existing wall locations did another set and another get. So that was doing for each connection name, and it ranges over the main NCI SQL databases. So this times 2, so 2 sets and 2 gets. So here we do a set, and then we do 2 more sets and 2 more gets. So this was 3 sets and 3 gets. And we replaced that with something that does a single set almost every time. So going from 6 calls to, and we eliminated the get too. So going from 6 calls to 1 call, even though they were in a multi, made a big difference. And the idea behind this optimization was that this thing used multiple keys, so it was a structured object basically, and it had multiple fields, and every field within the structured object used a separate Redis key, and that's why you needed to do multiple set and get calls. And we improved that by packing those fields together into a cookie and storing that as an opaque blob in Redis. And then the other thing we did is that because there was a set and a get here, and that is because we used the NX flag, which means that we only set if the key doesn't exist yet. So this get is meant to get back the current value, regardless of who set it. So we changed that with code that does the set. And if the set succeeded, we don't need to read back the value we just wrote because we just wrote it. And that eliminates the get call. So that's how we went from 6 calls there to 1, because almost this set almost always succeeds. So this pessimistic, let's read back the value that is there, makes a lot of sense, but in the end, it was a lot of overhead. I mean, some things are just, you really need a multi. Like if you want to create a Redis data structure and make sure it has an expiry time, where it's really important that it has an expiry time, and you need to make an expire call, then the only way to do that really reliably is to group them together in a multi. So that makes sense. But if you, in this case of this code, what we really have is one object with 4 or 5 fields, and we are scared that some of the fields disappear, or we want all the fields to be created at the same time. So we use a multi to create 4 or 5 different fields. And they should all exist or not exist. And a better solution there is to say, well, if all these fields need to exist or not exist, then we should group them together in a single write and do that instead. So that to me is a suspicious use of multi.
I guess one other way to approach this would be Lua scripting, which in this case probably still not the best way, but it can be an alternative to multi also.
Yes, that's another thing I forgot to mention, but we did use multi here because there is a case where we want to read this cookie and update some values conditionally, and we made a Lua script for that. And because we used message pack, Redis can unpack the cookie, and we can look at the cookie and do some stuff with it and then write it back. I haven't gotten around to doing to investigating where the tipping point is, where a Lua becomes better than a multi, because Lua has its own overhead, because you need to start up the Lua interpreter. Not completely start it up, but there's some setup and teardown overhead to using Lua on Redis, but you are saving all the network I/O. So there is if you're using a multi, consider using Lua or Benchmark, which of the two is faster, and Lua might be faster. But just doing everything with one call without any scripting is still better. Another example I wanted to point out is here in this Redis set cache class we use, where we run into the problem that you can't store an empty set in Redis. So if you have a Redis set and you delete the last element, then Redis says, well, I'm going to garbage collect the key. So you cannot distinguish between the key exists, but the set is empty, or nobody ever set the key. So this method is here to distinguish between that and say, well, is this value in the key, and is it, and if not, why is it not there? Right? Is it not there because the key doesn't exist, or because the key contains other stuff and just not the value we care about? And this is a valid way to solve that problem with a multi, but the problem is now you're using a multi every time. And you can also solve this by saying, we're going to create a special element that cannot exist in this set. And every time we create the set, we insert this sentinel element. And if we want to do an existence check for a value, we use sysmember, you can request multiple values. So you can say, does the sentinel exist, and does the value I care about exist? And then if the value exists, then the value in the sentinel come back. If the value does not exist, but the set exists, the sentinel comes back alone. And if the set does not exist, you get nothing. So then you only need one member check, and you don't need the multi anymore. So there's different ways of solving these problems. Of course, you need to solve another problem, which is to make sure you have a sentinel which cannot exist in any of the values you store, but you can do that by doing escaping. I don't know if this is followable when I say this, but you see that there's a empty Redis. It's just a thing Redis does, right? If you have sets or lists or hashes, and once they become empty, you can no longer tell if they exist. Empty sets and empty lists don't exist in Redis. So if you want them to exist, you need to make sure they're not empty at the Redis level. That's a trick, and we don't call this often enough that I think it's worth it to optimize this. But to me, this is a use of multi that is not necessary. Complex data structures are also suspicious when I'm looking to optimize queries, because it's just very appealing to use all the data structures, right? Redis has really cool data structures, and if you're a developer, you just like, oh, I'm doing this, and this looks like a hash, or this looks like an ordered set, and let's use one of those. But you don't always need the complex data structure, and ultimately this is a design problem where it's difficult to give rules about what to do. But the more structure you push, there's a cost to putting structure into a database. So storing an opaque blob like a session cookie in Redis is always going to be faster than saying, well, if you think of the session of a Rails app, right? That is a key value store. So you could say this is a Redis hash, and we're just going to store it as a Redis hash. And every time we fetch the Rails session, we do an hgetAll, and we get all the keys and values back. But guess what? That's really inefficient, and you should never do that. And you should instead present this structured object as an unstructured opaque blob to Redis, because then Redis is fastest, and you don't incur this overhead. So anything that is not a string key in Redis, ask yourself, what operations are we doing on this data structure that we really need this data structure for? And if you can avoid them, then that's probably going to be faster. The moment you have a complex data structure and you're often fetching the entire data structure, that is a red flag. Although in the case of that set cache, membership checks are a very good reason to want to be using a set, right? Because you don't want to have to fetch the entire set to check for membership. So that's a valid use of a data structure. Slow requests are suspicious. So, and slow requests, if you look at these graphs, can be recognized by seeing a command where the operation rate is low. So it means it's somewhere down here. There's always this long tail of things that you can't see. But it's somewhere near the top of the total latency, or maybe it's like way above the rest. So if you see that, you see something that is, on the one hand, not happening a whole lot, but every time it happens, it takes a lot of time. That is super suspicious, and then you need to find out why that is. One way is to look at TCP dump captures, or to fetch keys and see what's in them, for which you need console access at the very least. Or you can look at the flame graphs and see where time is spent in the flame graph. And I don't have an example up here. Although I think I had one somewhere about, yeah. So in the case of Q per shard, we had some flame graphs, and this is actually about something else, but it makes what you can see here is that blocking pop generic command takes a long time, and no client blocks on keys takes a long time. And so blocking this command, why is this taking a long time? And the in this case, it was an n times m problem. Slow log is it shows you outliers, I think. So I don't think like these BR pops. Thank you for whoever posted that. But if we look at this, sorry, where did the picture go? Screenshot this one. These blocking pops were not going to be in the slow log. Maybe because they're excluded because they block, or but yeah, I don't know how. Yeah, I can't remember a problem I worked on that was driven by outliers in the slow log. So that doesn't mean the slow log isn't useful, it's just that I never got to use it. Maybe somebody else from scalability can remember a case where the slow log directed us to something. I suppose if say like these sets of branch names or whatever, if they're huge, or if they're huger than we think they are, then the outliers will show up in the slow log, so it can give you a hint of a problem. But yeah, so just being slow in terms of the metrics is interesting. But you can't always find something like that. But if you find something like that, that is worth looking at. And of course, slow also means that in this thing, right now, everything looks roughly the same size, but sometimes one thing is like 5 times bigger than everything else. And then that is an obvious target for optimization. And,
yeah, I don't recall ever really using the slow log for everything. And I guess the Redis query interface isn't really advanced enough to allow you to write slow queries most of the time, right? It's not like SQL where you can write a really slow query. So the issue usually is a combination of slightly slower requests and then just a lot of them. So volume usually play a big.
Usually it's a multiplicative problem, right? So it's
the multiplicative problem that we, for example, see in the slow log is iterating a very large set, for example. What was it? Deleting an element, a specific element from a set.
The tags cache
Tag and branch
the
names, exactly.
branch cache. Yeah, those examples where I think the reason we found them was because of the slow log.
Yeah.
But those are, like you said, it's not a super common approach.
Yeah. Well, it's there. And
if it's the same
it's useful.
thing, the n is too large.
Yeah.
Yeah.
Yeah. So I get to one of the next one, which is n times m problems, which I think we've seen a bunch of, where things can get slow if you have something that is large in one way multiplied by something that is large in another way. And I need to put large in air quotes because at what point large is a problem is hard to say in absolute terms. So a good example was the Psychic using many queues. So when we ended up with an architecture where every Psychic worker had its own Redis list acting as the queue. And then the one large number was the number of Psychic processes, and the other large number, which was like in the hundreds, and the other large number was the number of queues, which was also in the hundreds. And we were doing, so the blocking pop commands were slow because they were doing work proportional to hundreds of queues, and we were doing that, and hundreds of Psychic servers were doing those slow blocking pops. So that was blowing up the problem, this multiplicative effect. And empirically, usually you can solve the problem by bringing down one of the large numbers. So saying all Psychic servers have to do blocking pop, but that's okay, as long as they don't do it on a lot of queues. Or in the case of Scikit cron, you have so Scikit cron stores a list of all cron jobs that exist, and when your Scikit server process boots, it starts a thread that pulls this list and makes sure that these jobs all get to run. Or just it looks at them and says, does any of these need to run now? Well, let's schedule one. So the list of cron jobs that the application device is large, and the number of Scikit processes is large. So they were all fetching this large list, and then it ended up happening a lot of times, and that was I don't know, yeah, using 10 percentage points or something of Redis server CPU, and it was completely pointless because like only one process needs to schedule the cron job to make sure that it happens. So there's no point in having hundreds of things duplicating the work that really only one needs to do. And we improved that situation by changing the well, still hundreds of Scikit processes are polling this list, but the frequency that they poll at is lower. So the effective number is a number of times that we need to fetch this large list of cron jobs is brought down, and then it was that made a big difference. And Igor, add another example. Can you speak to that?
This was an internal one in Redis itself, which was kind of amplified due to us having a lot of clients, which I guess a lot of other folks don't necessarily run into. But yeah, it was kind of a nice fix in Redis upstream itself that our report was able to facilitate.
So what were the N and M in this case? So clients, and the other one was
the number of
it was clients times clients. Or who was so a large number of info calls, and every info call went over the clients?
Yeah.
And how did we fix this, or how did upstream fix this?
If you scroll down, there's a commit that you can click on. I think it was the second.
This one?
Yeah, I guess. Yeah.
Or
no, that's the one. That's
yeah.
the one. So yeah, basically amortizing the call instead of doing it all in one go. So amortizing and memorizing.
Okay. So that over time, repeated info calls update the number.
Yeah, well, I think it happens in a background.
It's incremental.
Yeah.
Yeah. Right, it's cron. Okay, it's a cron. And this. So it's this function, get expensive clients info with a misspelling in it. That does this work incrementally.
Yeah.
I think this should be an E, but oh well.
Yeah, not sure.
Yeah, so there was an existing mechanism for this. Cool. Yeah. And this is not a unique problem for Redis. This is just an algorithmic problem, but I guess because our infrastructure is large enough, we see these problems because anything that's driven by the number of processes that do something will create a multiplier. Yeah, so those were some of the principles that I made up after the fact. And then yeah, we talked about some of these examples already. So in the case of duplicate jobs, instead of saying we have an object with many fields and we store the fields as separate Redis keys, we collected them in a single cookie. And we still didn't want to make it completely opaque, so Redis can unpack the cookie from a Lua script and modify it and rewrite it, but that only happens rarely, and that made a nice improvement. We had another funny problem with rack attack, which is the rate limiting middleware we use in GitLab, where we were passing through many abstractions layers to update counters in Redis. And one of these abstraction layers did not take into account that if you increase a key in Redis as a numeric value, that doesn't change the TTL. And so you only need to set the TTL. And the way rack attack works is that a key has a TTL that's known at the time it's created, and it never changes. But every time we incremented the counter, some abstraction layer was pessimistically setting the TTL again every time. And we got rid of that by removing some of the abstraction layers and writing something that omits the TTL call. Actually, the expire call that sets the TTL, or I forgot the details already. But it was abstraction layers weren't helping, which again, I guess is a general problem. Like if you do everything through Active Record or through ORMs on a SQL database, you sometimes also don't get efficient queries, and you need to just write SQL yourself. So it's the same kind of problem. And this showed up through TCP dump because we could see all these calls happening clearly. But it also showed up in the request counters because the number of expire calls didn't make sense, so the number of TTL calls. And yeah, so in the case of Kuber shards, one technique, this was a team effort, and we approached this from multiple angles, and this was also experimentally validated by Craig Miskell at the time. But looking at it, this was also something you could see by looking at the source code. So in the flame graphs, you could see time spent in these functions block for keys and unblock clients. And then if you start reading the source code, then you start seeing things like, hey, this is a loop over the keys. So this does work. And in this case, keys were psychic queues, of which we had 400. So this is a loop over 400 things. And so whatever we're doing here, here you see the multiplier. And so when looking through the code, loops are always good to look at because they loops are bad. Well, loops are necessary, but they act as multipliers. Yeah, so now I've talked to the bottom of this document. Any more questions or comments?
You know our workloads pretty well. What's the next workload that we're going to probably have to figure something out for that we can't, like, that's not easy?
I think I need to contradict you on the first point. Like I forgot or I stopped looking, so I'm not sure right now what the apart from what we're doing with Redis cluster, I think the most impactful thing we've been doing is functional sharding and just lifting big things and moving them around.
I'd argue like we've done that a few times, but comparison like effort and yeah, results, the smaller things that you've brought up here, Kuber shard was a large one, the duplicate jobs cookie, the rack attack thing and so on have moved saturation dates out way more for way less effort than a functional shard.
Yeah, well, the problem is I liked looking at these things, and everything that looked like I could fix it, I just went ahead and fixed, and then we all said, let's worry less about Redis right now because it seems okay, and I stopped looking. So I think the ones that look fixable, I've probably gone in and fixed because I couldn't help myself. So I'd have to start looking again to see if there are good candidates. And sometimes these things don't work out or don't deliver as much value as you hope. Like one thing that was interesting was the thing with the pub/sub for the CI runners and workhorse. So we were using the application was doing something really inefficient, and we changed how that, but to push messages from Sidekick to workhorse, where every message had to get delivered to every workhorse process. So there was a n times m problem again, because you have n messages and m Sidekick and workhorse processes, and you had this multiplier. But when we changed that, some of that work was happening in IO threads, so we didn't really see the payoff. And in order to stop broadcasting to everything, the workhorse processes have to subscribe and unsubscribe from channels, and that created work. So in the end, the payoff wasn't as big as we hoped. But I think your point still holds, Bob, that sometimes these changes are cheaper to make than setting up new infrastructure, which is, I guess, also one of the reasons I liked going for these things. Well,
I had one more.
Yeah.
So yeah, I shared an investigation from like 3 years ago, and we went down so many like false paths, and really refined the analysis over time. I think this was like a multi-week investigation, and this was kind of the highlight, like the smoking gun, where there was bursty workload happening once every minute. And it's really hard to see with our existing monitoring, because even for CPU utilization, our Prometheus metrics are only sampled every 15 seconds. And so we could see a slight burst. But if you were to actually run like a VM stat on the box and look at the CPU utilization every second, it would burst to 100% for like 5 or 6 seconds at the beginning of every minute, and then drop down. And it was basically impossible to see with the existing metrics that we had. And so one useful way
what caused this?
It was a endpoint, like a list endpoint that was doing 7 calls for each repo listed on the page. And there's like 25 or 50 repos per page.
Mm-hmm.
And so like 50 times 7 was enough of an amplifier to just flatten Redis in this case. And so one thing I wanted to highlight in terms of tooling, I mean, we used a whole bunch of stuff. We used TCP dump analysis that you already talked about. But what I wanted to mention specifically is Flamescope, which I don't think we covered, or maybe we did. It's a way of looking at a CPU profile over time. So you showed flame graphs.
Yeah.
And the flame graph is going to be like a summary of the entire duration. So 30 seconds or 1 minute. But it means you don't really see the bursts, right? And with Flamescope, you can select subsets. So show me only these milliseconds of the profile. And that can really help identify where time is being spent during some of these shorter bursts. So yeah, just wanted to highlight that.
Yeah. So I suppose what was unusual here was that the bursts were saturating Redis, but was Redis saturating on so if you would have looked at the second accuracy, then you would see the bursts. But
Yes.
if you look over a longer window, then you effectively get an average, and the average was not saturating. Is that what was happening?
Yep. Yep. Exactly. So, like spending during the 15-second sampling window, we spend half of it being completely saturated, and then half of it being like at 50% or whatever. And so that averages out to significantly less than 100%.
So, and 50, yeah. I'm wondering if because we run our servers at higher utilization now, if it would also have shown up in the average. But yeah, that's
The problem we had with the evictions at max memory last year is very similar, and it also didn't really show in average. The saturation was visible in app dexes, but not in CPU graphs.
yeah. Well, I was wondering if it was the same thing, because that also used the term microbursts, but I guess that's because Matt was
I think
also
it's the same
involved there, and
person, yeah.
it's the same people finding the problem. And what was interesting there was that we learned that Redis isn't good at LRU eviction, and we shouldn't let it do that. That's why I was curious with Igor's example from just now, if it was about the same thing or a different problem. So this was about, it was a different problem, and it was about a specific kind of traffic. Yeah. Wow. Thanks for sharing that. I wasn't there for that investigation. Okay, well, if we don't have anything else in terms of questions, then we've been going for almost an hour, then I think it would be good to wrap it up.
Thanks, Jacob.
Thanks for joining,
Thanks for
everyone.
this. This was a lot of fun.
Now, how do I stop the recording?